Finding the rule for a quadratic sequence is a challenge, but there is a shorter way. Check it out here in Mathematics of Engineering. As a review, quadratic sequence does not reflect a constant difference in the first attempt, but rather, the constant difference will show up at the second level. With the sequence 5, 8, 13, 20, and 29, the first difference shows different values, but then, taking another attempt shows that the second difference is already constant. Let's break down the sequence into parts for us to find the general formula. We write the terms as u sub 1, u sub 2, and so on, and designate the first difference as d. That is, u sub 2 minus u sub 1 is d1. U sub 3 less u sub 2 is d2. Then u sub 4 minus u sub 3 is d3. Then again, the second difference is taken as d2 minus d1. We notate it as d prime 1. So d prime 2 is d3 minus d2. Since the sequence is quadratic in nature, we can presume that the nth term is equated to a times n squared plus b times n plus c, where n is the number of terms in the sequence. The task we are to do is to look for the values of a, b, and c, and they are found in a particular pattern. Start solving a by equating 2a to the first term of the second difference. We notated this as d prime 1. Then b is computed by equating 3a plus b with d1. Then lastly, c is solved by equating the initial term by a plus b plus c. Example 1 has the sequence 3, 7, 13, 21, 31, and 43 to showcase the method. We start by looking for the difference, so begin with 7 minus 3 is 4. Then 13 minus 7 is 6. 21 less 13 is 8. 31 minus 21 is 10. And 43 minus 31 is 12. This is the set of the first difference, where the terms are deviating. Then proceed to the second difference with 6 minus 4 is 2. 8 less 6 is again 2, so with 10 minus 8, and also 12 less 10. Having a constant difference at this point confirms that we have a quadratic sequence. Again, the general formula is that with a quadratic equation, and we have to look for a, b, and c. A is determined by equating 2a to the first term of the second difference, that is 2a is equal to 2. Divide both sides by 2 to isolate a, and we get a is equal to 1. B is also computed by equating the first term of the first difference with 3a plus b, that is 3a plus b is equal to 4. Then by substituting a, which is 1, into the formula, we have 3 times 1 plus b is equal to 4. Then transpose 3 to the constant side to have b is equal to 1. And then c is taken by equating the first term of the sequence with a plus b plus c. Thus we have a plus b plus c is equal to 3. Substitute values of a and b into the equation to get 1 plus 1 plus c is equal to 3. And again transpose 2 to the other side to get c is equal to 1. Now we are ready to plug the values into the equation. Thus u sub n is equal to 1 times n squared plus 1 times n plus 1, which is simplified as u sub n is equal to n squared plus n plus 1. Let's check if indeed we have the right rule for the sequence. With n equal to 1, u sub 1 is computed as 3. Then at n equal to 2, u sub 2 is 2 squared plus 2 plus 1, which is 7. At n equal to 3, we can solve u sub 3 as 13. U sub 4 is also taken with 4 squared plus 4 plus 1 giving 21. At n equal to 5, we have u sub 5 as 5 squared plus 5 plus 1, which is 31. And then n as 6 yields u sub 6 as 43. These are the terms that we have in the sequence, so it is verified that the rule for this quadratic sequence is n squared plus n plus 1. Here is another example for you to master the process. With the sequence 1, 0, -3, -8, -15, and -24, we first look for the first differences, starting with 0 less 1, which is -1. -3 minus 0 is -3. -8 less -3 is -5. -15 minus -8 is -7. And -24 minus -15 is -9. Then continue with the second difference. That is starting with -3 minus -1, which is -2. -5 minus -3 is -2. -7 minus -5 is -2. And -9 less -7 is -2. Having a constant -2 for the second difference verifies the sequence as quadratic. So the nth term as a n squared plus b of n plus c is used. So for a, we use the first term of the second difference and equate this to 2a. That makes the equation 2a is equal to -2. Then by dividing everything by 2 makes a equal to -1. b, on the other hand, is computed by equating the first term of the first difference with 3a plus b. So the equation is 3a plus b is equal to -1. Now plug the value of a to the equation, making it 3 times -1 plus b is equal to -1. -3 is transposed to the other end of the equation, making b equal to 2. For c, the expression a plus b plus c is equated to the first term of the sequence. So the resulting equation is a plus b plus c is equal to 1. And by substituting the values of a and b makes it -1 plus 2 plus c is equal to 1. Simplified as c is equal to 1 minus 1, or that is c is equal to 0. By placing all values of a, b, and c into the equation, we get -1 n squared plus 2n plus 0, which can be shortened as -n squared plus 2n. Check the validity of the equation by plugging n values, so start with n equal to 1, giving a sub 1 as 1. At n equal to 2, u sub 2 is -2 squared plus 2 times 2 to give 0. Then at n equal to 3, u sub 3 is -3 squared plus 2 times 3, which is equal to -3. With n equal to 4, u sub 4 is computed as -8. Then with n as 5, u sub 5 is -5 squared plus 2 times 5, giving -15. Then with n equal to 6, u sub 6 is -6 squared plus 2 times 6, giving the last term as -24. Having coincident values for the terms confirms that the equation for the sequence is indeed -n squared plus 2n.